Today we're going to talk about a new topic, and we're going to cover something called molecular formulas. And in order for us to understand molecular formulas, we first have to review empirical formulas. So, empirical formulas, the empirical formula for a compound is the formula with the smallest whole number mole ratio of the elements in that compound. The ratio is represented as subscripts in the chemical formula and can be calculated from percent composition data. So that's what we've done so far, is take percent composition data, convert it to moles, and then determine a ratio. Now, this might surprise you, but substances with distinctly different properties, so completely different chemicals, can actually have the same percent composition data and the same empirical formula, but could be completely different compounds. So how is that possible? Well, remember that the subscripts, so those little numbers we read at the bottom, in an empirical formula, indicate the smallest whole number ratio of moles of the elements in the compound. So what that means is that we're looking at the smallest possible combination and ratio of those atoms. The simplest ratio does not actually always indicate the actual ratio in the compound as it's found in nature or in the lab. So when we work with a chemical, while its empirical formula might be CH, when we work with it in lab, it might actually be C2H4 or C2H2, excuse me. Now, what that means for us is that the empirical formula for multiple compounds can be the same thing, but we need to be careful that we don't mix up the compounds or the chemicals when we're trying to determine the identity of the chemical. So, there's this thing called a molecular formula. Well, compounds are actually identified by their molecular formulas, not their empirical formulas. Molecular formulas specify the actual number of atoms of each element in one molecule if it's a covalent compound, or a formula unit if it's ionic, of the substance. So example, acetylene, which is a gas, and benzene, which is a liquid, they have the same empirical formula of CH, but they have way different molecular formulas and way different properties. Obviously, one's a gas and one's a liquid. The empirical formula may or may not be the same as the actual molecular formula. So in the case of acetylene and benzene, as seen on the previous slide, the molecular formulas for those are different and they do not match up with the empirical formula. If the empirical formula is different from the molecular formula is always going to be some multiple of the empirical formula. So for example, hydrogen peroxide, the molecular formula is H2O2, but its empirical formula is HO. Now, the difference between those is literally you take H times 2 and O times 2 to get H2O2, because when there's no subscript, it's an understood 1. So to determine the molecular formula for a compound, the molar mass of that compound actually has to be given to you in the problem, or found in lab. This molar mass must then be compared with the mass represented by the calculated empirical formula. All right, so what do I mean by that? Well, if I tell you that the molar mass of acetylene, as it's found in lab or in nature, is 26.04 grams per mole, and we know its empirical formula is CH, because that's all information that we've either calculated or I've given you. Now, what you need to do is compare the molar mass you're given to the molar mass of the formula you have calculated. So the formula we've calculated has a molar mass of 13.02 grams per mole. So the next step says that dividing the actual molar mass, so 26.04, by the mass of the empirical formula, 13.02, indicates that the molar mass of acetylene is 2 times the mass of the empirical formula. So 26.04 divided by 13.02 equals 2. So what does that mean? Well, because the molar mass of acetylene is 2 times the mass represented by the empirical formula, The molecular formula of acetylene must contain 2 times the number of atoms, so carbon and hydrogen, as represented by the empirical formula. The integer, in this case 2, because again 26.04 divided by 13.02 equal 2. This integer is the factor by which the subscripts in the empirical formula must be multiplied to obtain the molecular formula. So if the empirical formula is CH, and we take C1H1, which is really what that's saying, and multiply each subscript by this answer 2, we get C2H2, which tells us the molecular formula. All right, so we have empirical and molecular formulas. An empirical formula tells you the ratio of atoms in a molecule or formula unit. It cannot be reproduced. So it's something like CH. A molecular formula tells you exactly how many of each atom are in the molecule as it's found in nature and can be reduced. So something like C2H2 can be reduced to CH. Now the example shown at the bottom here is that the empirical formula of sugar is CH2O, so they're not all ones, but still can't be reduced anymore. And the molecular formula of sugar we know to be glucose, C6H12O6. Well, in C6H12O6, all 3 of these numbers are divisible by 6, which is what gives you CH2O. So, some questions you might see would be, which of the following could be empirical formulas? Well, the steps that you need to take to answer this question is to look at the subscripts. So 2 and 4, are they, is one divisible by the other? Well, if we take 2 divided by 2, that's 1, and 4 divided by 2, that's 2, so that can be reduced. So this is not an empirical formula, because empirical formulas cannot be reduced. N3O6, well, both of those are divisible by 3, so that can be reduced. NO, just one of each, so yes, that is an empirical formula. H2O2, nope, it can be reduced, but HO cannot be. Another type of problem you might would say, determine the empirical formula for the following compounds. C2H4. So I'm going to take the smallest of those 2 integers, or the subscripts, and divide both of the subscripts by that number. So C2H4, divide both by 2, so C2H4, divide both by 2 to reduce, and we get CH2. So that was number 1. Number 2, C6H8O6. Well, the least common multiple, or the factor that factors into all of those, is 2. So if I take C6H8O6, divide each of these subscripts by 2, I get an empirical formula of C3H4O3, which cannot be reduced anymore. All right, and then number 3, we have C10H8, again, divisible by 2, so C10H8 divided by 2 gives us an empirical formula of C5H4. So when you find out your empirical formulas, you need to make sure that this is the most reduced form. If you use the wrong factor, or you divide by the wrong number and you still get an answer that is divisible by more, keep going until you reduce it until it can't be reduced anymore. Alright, so lastly, let's talk about a couple example problems. A compound with an empirical formula of C2OH4 has a molar mass of 88 grams per mole. What is the molecular formula of this compound? Alright, so let's talk about the steps. The first thing we need to do is compare the actual mass with the mass of the empirical formula. So let's over here calculate the mass of the empirical formula. So there's 2 carbons, so 2 times 12.01 plus 1 oxygen, so 1 times 16.00, plus 4 times 1.01. So we have 24.02 plus 16.00 plus 4.04. And that gives us a molar mass for this guy of 44.06 grams per mole. So now what I need to do is take this guy that I'm given, the actual molar mass, divide it by the molar mass of the empirical formula, and that will give me the integer that I need to then multiply the subscripts of the empirical formula by. So plugging this in, we have 88 divided by 44.06 gives me 2. So now I need to look at my empirical formula of C2OH4 and take each subscript and multiply it by 2. So that would become, if I essentially multiply this by 2, it would become C4O2, don't forget about that, H8. So this would be my molecular formula. I'm going to go ahead and solve this bottom one here, number 2, but I want you to either pause the video or work along with me to see if you get the right answer. So I'm going to work through it, but I'm not going to talk through it. So I solved for the molecular formula and got C2F2Br2O2. Now the last couple of problems that I want to go through with you are combining what we've learned in the past couple of lessons about empirical formulas and molecular formulas. So in the last set of problems, I gave you the empirical formula. Now we're going to take it one step further, and I'm going to go back to giving you, the percent composition data and ask you to calculate the empirical formula, then compare that to the molar mass of the molecular formula to tell me the molecular formula. So this says an unknown compound was found to have a percent composition as follows. What is its empirical formula? If the true molar mass of the compound is 166.22 grams per mole, what is its molecular formula? So backing up to empirical formula jargon, we need to first assume 100 grams. So each of these percent signs is going to become a gram symbol. So 47.0 grams of potassium, 14.5 grams of carbon, and 38.5 grams of oxygen. Alright, so 1 mole of potassium is 39.10 grams of potassium. 1 mole of carbon is 12.01 grams of carbon. And 1 mole of oxygen is 16.00 grams of oxygen. So I'm going to do that math. I get 47 divided by 39.10 equals 1.20, 14.5 divided by 12.01, and I get 1.21, and then 38.5 divided by 16, I get 2.41. So I pick the smallest of these three numbers, which is 1.20, and I divide each of these by that number. So that leaves me with 1, 1, and 2. So my empirical formula then is, let me see, I'm going to draw a little arrow up here. My empirical formula is K1, C1, O2. Now, the next step says, if the true molar mass of the compound is 166.22 grams per mole, what is its molecular formula? Well, first I got to calculate the molar mass of the empirical formula. So 1 potassium is 39.10, 1 carbon is 12.01, and 2 oxygens is 32.00. Add that together. 39.10 plus 12.01 plus 32 is 83.11 grams per mole for this guy. Now remember, the steps were to take the actual molar mass divided by the molar mass of the empirical formula defined in integer. So 166.22 divided by 83.11 equals 2. So we need to take every subscript in our empirical formula and multiply it by 2 to get our molecular formula. So our molecular formula then is K2C2O4. And that is the end of the problem. Lastly, I'm going to go ahead and work through this problem again silently. I want you to work it out, see if you get the same answer, and then we can either wrap up the lesson or you can work back a little bit and go through this again. All right, so finishing out the problem, the empirical formula I got C5H7N, and the molecular formula I got C10H14N2. Okay, so that wraps up this lesson. So if you have any questions, feel free to shoot an email. Otherwise, go ahead and continue working on the practice problems. And all right, that's it. Thank you.